Welcome back, everybody, to another episode of Security Simplified. Tonight is episode 6. We'll be talking about what is an IP address. This is picking up from episode 5, where we learned the importance of networking fundamentals. And tonight we're going to go a little deeper. We're going to take a look at some packet captures. We're actually going to inspect some network traffic and unpack the packets themselves. Joining me tonight is my wonderful co-host and networking ninja, Evan Francine. Evan, how you doing tonight?
Good, man. Thanks for, it's good to do another episode. So we're going to, for the purpose of, packet capture, we might as well use, I think the most popular packet capture program in the world. It's free. It's also open source. So we're going to go to Wireshark and use that one. To get it, just go to wireshark.org/download, and you'll find a whole bunch of different packages that you can install there. Now, I'm on a Macintosh, so I'm going to use the Mac OS Intel. You'll have to know whether you have the M1 chip or the Intel chip. Now, I have the Intel chip, so I would choose the Intel 64-bit package and download that. I think it's about 128 megabytes, so not too much. And once you get it, go ahead and open it, install it, then you're going to get this, right? And this is, what it looks like when we've opened it. Now, if you don't see this, and what I'm pointing at for people that are just listening, I see my interfaces listed here, and one of the interfaces, the one I'm actually going to capture on, is Wi-Fi :EN0. EN0 is the number assigned by the operating system. You can see I've got some traffic already there when I open it, right? That's just how much traffic it's seeing. Now, if I'm going to be capturing packets and I don't see anything on that sort of heartbeat line, that means that something's misconfigured, right? Now, you can go down here to where it says Learn, and there's a user's guide. Usually it's because you missed an install or you didn't have permissions to capture packets. That's usually why you see the flat line. But if you go to the user guide, right within the interface, you'll be able to find the answer what you're looking for. So having said that, I'm going to go ahead and just capture packets. So the way I do that, just double click on it, on the interface, and I'll see a whole bunch of things scrolling on my screen. These are the packets. Now, when you're doing packet captures, it puts your interface in what's called promiscuous mode. Doesn't mean that my packet has unprotected sex often. That's a different kind of promiscuous. This just means that it's listening to all the traffic and it's going to process all the traffic that it sees. When a network interface isn't in promiscuous mode, it only processes the packets that are meant for it. So a little bit different. Now I'm capturing on a Wi-Fi network, so I may not see all the network traffic. Right, I might see only the traffic that happens to come towards this interface. So important things, more so when you're capturing on a local area network, a wired connection. If I'm connected to a switch, the way networks work, I'm only going to see the network traffic that comes through that switch port, which won't be all the network traffic on the network. I would use something either like a hub, something that doesn't filter traffic, or I would configure my switch to forward all network traffic that it sees through my port. So we've been capturing packets for a little bit here. If I want to stop it, I just click the red square, and now I've stopped capturing packets. You can see down here on the bottom a few statistics, 75,436 network packets. So quite a bit of stuff, quite a bit of few things, whatever, going on my network. All of those are being displayed 100%, so I didn't run out of buffer here. Because if you let this run forever, eventually it's going to roll on itself. That's a configuration change that you can make. But I've got all the packets that I was looking to capture. I'm going to go ahead and expand this. Anything you want to add, Ryan, before I dig into a packet?
When we're talking about interfaces, we're referring to either a wireless connection, so a Wi-Fi connection, or we're referring to a LAN connection, that hardwired, to the network interface card. And there can be virtual interfaces as well. So when you're using a tool like Wireshark, and you see this big list of interfaces. Some of those interfaces are virtual, some of them are loop back. Like Evan said, we want to watch for that heartbeat. But just know there are multiple types of interfaces within a given network.
Yep, absolutely. In the things, so one of the questions I think, which sometimes we just take it as obvious, why would I capture packets to begin with? Well, one, if I might be doing it just for educational purposes. I'm just interested in knowing what happens on a network. Sometimes I'll do it when I'm trying to, something unusual maybe is happening, so I'll use it for troubleshooting purposes. Uh, another reason is I might do it for an investigation. I think something funky is going on my network, and so I want to dig in. I want to see what's actually going on. So I don't just want to assume that everybody knows why I would capture packets, but here we're just capturing packets for education purposes to show you guys what it looks like. So you can see in this top window, so there's 3 windows in the default sort of how things are configured in Wireshark. The first column is the number. This will be a sequential number. Every packet that Wireshark sees, it's just going to add a 1 to it. And so that's the sequence. We've got a time. This will be all the way down into the milliseconds. Somebody, you can see the point, whatever. That first number is the actual number of seconds, and then, the decimal point. We've got 6 decimal points by default. Then we've got source and destination. Those are IP addresses. We've talked about what an IP address is. So the source IP address, the destination IP address, the protocol that's being used, that's the next level protocol. So IP, you might remember from the last couple of episodes, IP works at layer 3 of the OSI model. It works, TCP and UDP work at layer 4 and 5, essentially. But there's that handoff there. So here's the IP address. That's a logical address. The protocol that's being used, so usually we'll see TCP, UDP, you see an SSL v2 here, that's secure sockets layer. You see the packet length. Sometimes we see packets maybe on the network that are jumbo packets. That's a telltale sign that something is malfunctioning on the network. Typically, everything on the network, if it's functioning correctly, will play by the rules, right? And the length of the packet will match what's called the maximum transmission unit, the MTU of the network, right? If we see a big jumbo packet, oftentimes it's a hardware problem. Something's flaking, something's breaking. The length, and then info. Info is just some interpretation by Wireshark of what that packet's doing. That's what we see in that top screen. Now the middle one is where we're going to dig in. That's where you actually get into the contents of individual packets, which gets pretty interesting. And then the bottom window is really in hexadecimal format. It's more of a raw format of what that packet looks like. Machine readable, certainly more than human readable. We don't pay a lot of attention usually unless we're getting really deep in that bottom window. So anything to add to that, Ryan, before I dig into a packet?
No, I think that was a really good overview of what we're looking at here, and looking forward to getting a little deeper.
All right. Well, I'm going to skip this first one. This first one's got a source that's external to my network, and I'm going to use this second one. Actually, I'm going to use the third one here. I think the third one looks interesting. So this third one has a source IP address of 192.168.0.98. That's my IP address. That's this individual system that I captured packets on. It's got a destination of 54.192.131.90. We might have covered briefly what an internal what an internal non-routable IP address is and what an external routable IP address is. The 192.168 dot whatever space is not routable, so you won't see that on the internet ever. You'll see it on your local networks typically. That 54.192.131.90, that's a public IP address. That's a routable IP address. I know that that's probably on the internet. So let's go ahead and break it down. Now, when you read a packet on the OSI model, we're gonna unpack it from the top down. I always like to go that way, which is the reverse of what you're going to see in the window here. So from the top down, we've got transport layer security is the first layer. Then we'll go down a little bit. It's using transmission control protocol. The source port is listed right here, 63667. Now that's going to be a number. It's always going to be a number between 1 and 64535. That's the entire space that the computer can use to address this packet or any packet. That's that packet over 1024. So you might remember from another talk that we had that all the packets or source address, IP, whatever, port numbers between 0 and 1024 are called assigned ports. Usually you don't see those as source ports. Usually you see those as destination ports. Some number between 0 and 1024. Now there's always exceptions, but typically, so if I saw a source port here of, let's say, port 80, that's unusual. I shouldn't have seen a source port on my computer of port 80. Something's funky there. I should see something over 1024. And here I'm seeing 63667, which is assigned randomly, right? It's just a way that when your computer gets that network traffic back, it knows where to give it to, where to hand it off to. It's keeping track of what source ports it's using and what destinations it's using. So that's what that's used for. The destination port, 443, that's SSL or HTTPS. That's a secure sockets layer. It's typically a website that I'm visiting that is a secure connection. It's encrypted. The sequence number, that's to put the packet back together again. So as your computer is trying to put all these things back together again, these packets won't come back, and they won't get there all at the same, all in order. The way the internet works is some packets will get routed this way, some might get routed that way, some will arrive before other ones. That sequence number helps the computer put them all back together again so that it's a cohesive communication and not just spotty all over the place. We've got an acknowledgement. That means the acknowledgement flag is on. This is what's called an ACK packet. And then we've got a length, the 1428. Digging deeper into that, source port, destination port, stream index not being used in this packet, acknowledgement numbers. This is all stuff to put the packet back together again. The flags is interesting. I always like the flags to see what flags are set. What flags are used for is it communicates the intent of this packet to the receiver. So when you start, for instance, a TCP, you'd only see this in TCP. These flags wouldn't be set in a UDP packet. UDP is connectionless, meaning there's no acknowledgments that happen. It's just kind of best effort delivery on the network. Whereas TCP is connection oriented. It's much more reliable. There's a little bit more overhead, but that's what we're seeing here is what flag is set in terms of what the intent of this packet is. So in this one, only the acknowledgement flag is set, which means that this is just an acknowledgement of data that I already received. So I'm essentially telling the other computer that, hey, I got what you sent me. And the computer's keeping, the other who you're communicating with is keeping track of that, because if it doesn't get an acknowledgement, it's going to assume that it needs to resend that traffic. It didn't get there, right? So that's, part of this, the rules of communication that are happening on the network. Windowing, again, that's used for determining how large the packet can be. How much can I take from you in my buffer before I'm expecting something else? Window size is used for that. Timestamps, payload. The payload is interesting because that's got the actual data in it. So lots of really cool things to look at, and there are I'm covering a lot of things really quick. The best thing for you to do is on a computer that you have permissions, so you don't want to do this on a work computer that you don't have permission to work on, install Wireshark. Do this yourself. We'll come back to this. Refer to the video that's online at YouTube, Security Studios channel, or re-listen to the podcast so that you can kind of follow along with what I'm actually looking at. But that's the best way to learn, packet capture is to capture packets yourself. And I'm going to go a little quicker and get through the rest of this quick. We've got IP protocol version 4. We've got the header length, 20 bytes. All just really interesting stuff. There's my source and destination IP address that was shown in the other interpretation. Ethernet 2. So now Ethernet 2. So we started at 4.5. We went to Internet Protocol. That part of the packet, it's like stripping back layers, right? So we stripped off one part. We get into, what's happening at layer 3, which is IP. That's the IP portion that you're seeing there. And then we strip back again, and that's framing that happens there. That's layer 2. So I can see what type of, this is an Ethernet 2 packet. That's how it's framed. And now I've got this different address. That different address is called a hardware address. So the logical address, the IP address that was used at layer 3, needs to be interpreted to layer 2, which is the hardware address. So we resolve that. And you'll see, if you look through all the traffic here, you'd see a bunch of, where that says protocol, you'd see ARP, that's Address Resolution Protocol. That's the protocol that's used to convert a logical IP address to a hardware address. So I'm covering a lot, I get it. But like I said, I encourage everybody to capture packets. That it's fun once you really get into it. And then this last part is the actual framing of the packet for the network. The last part after that is sending it out onto the network. Real quick on this protocol, you'll see I've got TCP looking at a UDP packet. That looks totally different. If I scroll down here some more, I'll see some SSL version 2. That packet looks different. I'm trying to see it. I've got a stun packet. That's always kind of neat. Yeah, and I'm not going to see any ARP packets on this network because I'm not wired. If I was wired, I'd see my ARP packets doing that address resolution. So that's all I got. It's a lot of stuff, I know, but I do encourage, go to wireshark.org, download your own copy of Wireshark, capture packets on your own home network. I mean, it's really cool seeing what's actually happening on your home network. What's Alexa sending out to God knows where? What's Google Home sending out to God knows where? What are your kids doing on the network? Your packet filtering or your URL filtering stuff works kind of using this stuff too. So really interesting. Ryan, you got anything to add before we wrap this thing up?
Just, like Evan said, give it a shot, right? And know that, packet inspection is, within the world of information security professionals, this is a tool that is used both by the good guys and the bad guys. Very creative attackers can, use certain protocols and exploit them to exfiltrate data, DNS being the most common example, and they do that by stuffing the packet. So knowing how they work, knowing what those limitations are, what size generally should a DNS packet be? There is a range. It should be in that range. The packet itself is capable of holding more, which is why it's commonly used for that. So anyways, know as much as you can. Do encourage you to continue learning. Next week, Evan, what are we getting into?
Yeah, let's switch it up. Let's get into one of the things that I get questions on all the time, or I see it done poorly, is governance. When I say the word governance, some people shiver. And I think the reason why you shiver is because you've either been on the wrong side of bad governance or you've just struggled with it yourself. So we're going to cover governance. And that's going to be a lot of fun, man. I dig governance because I love holding people accountable. And you can't do that unless you establish good governance. So that'll be fun.
I'm looking forward to that. Well, thanks everyone for joining us tonight and tuning in. We ran a little long, but we look forward to talking to you again next week.
Have a good one.